For years, astronomers had a fairly simple picture of the early universe. The Big Bang happened. Space expanded. The first stars formed. Those stars gathered into small galaxies, and over enormous stretches of time, gravity slowly assembled those galaxies into the massive structures we see today. It was a gradual story. Simple at first. Complicated later. Then the James Webb Space Telescope began looking farther into the universe than almost any previous observatory could. And suddenly, that simple story became much harder to explain. Webb wasn't built merely to take beautiful pictures. It was designed to look backward in cosmic time. Because light takes time to travel, looking farther into space also means looking farther into the past. When Webb observes a galaxy billions of light-years away, it isn't seeing that galaxy as it exists today. It is seeing ancient light that began its journey billions of years ago. And that gives astronomers something extraordinary. A telescope capable of studying the universe when it was only a small fraction of its current age. Webb launched in December 2021 and began science operations in 2022. Its enormous primary mirror spans about 6.5 meters and is made from 18 hexagonal segments. But the mirror itself isn't the most important part. Webb observes primarily in infrared wavelengths. That matters because infrared light can travel through clouds of dust and gas that can hide objects from ordinary optical telescopes. It also allows Webb to detect extremely distant galaxies whose light has been stretched toward longer wavelengths by the expansion of the universe. And when Webb started examining the earliest galaxies, astronomers discovered something unexpected. Some ancient galaxies appeared surprisingly bright, massive, and structurally developed. They existed at times when the universe was still incredibly young. That raised a major question. How did so much structure appear so quickly? The answer is not necessarily that the laws of physics are wrong. It may be that our models of early galaxy formation were incomplete. Perhaps stars formed more efficiently than expected. Perhaps early galaxies accumulated matter faster. Perhaps black holes played a much larger role in shaping their environments. Or perhaps several processes worked together in ways that older models did not fully capture. This distinction is important. Headlines sometimes make it sound as though Webb has completely destroyed modern cosmology. It hasn't. Science doesn't work that way. Instead, Webb is providing astronomers with new evidence that forces them to test their assumptions against observations. And some of those observations are genuinely difficult to explain. One particularly strange discovery is a population of compact, reddish objects that became known as the little red dots. They appeared frequently in observations of the early universe and had properties that did not immediately fit neatly into familiar categories. Some may be young galaxies. Others may contain rapidly growing supermassive black holes. And one possibility that has attracted enormous attention is that their unusual appearance could be connected to the interaction between powerful black holes and dense surrounding material. If that interpretation is correct, these objects could help explain one of the biggest mysteries in modern astronomy. How did supermassive black holes become so enormous so early in cosmic history? Today, many large galaxies contain supermassive black holes at their centers. Our own Milky Way has one called Sagittarius A. But the problem is that astronomers have observed extremely massive black holes at very early cosmic times. That means some black holes somehow grew extraordinarily quickly. There are several possible explanations. Maybe massive stars produced unusually large black hole seeds. Maybe dense environments allowed black holes to consume matter at exceptional rates. Maybe black holes merged repeatedly. Or perhaps there are mechanisms of black hole growth that we still don't fully understand. Webb is giving researchers a much better view of these ancient systems. But the telescope isn't only investigating the distant universe. It is also examining objects much closer to home. One spectacular example is the Helix Nebula. Located roughly 650 light-years away, the Helix Nebula is the remains of a dying star. At the center is a white dwarf, the exposed remnant of a star that once resembled our Sun. Billions of years from now, our own Sun will undergo a very different but related transformation. After exhausting the hydrogen fuel in its core, the Sun will expand into a red giant. Its outer layers will eventually be expelled into space. The remaining core will become a white dwarf. The material released during this process will spread outward and become part of the surrounding interstellar environment. And this is one of the most important ideas in astronomy. Stars don't simply disappear when they die. They recycle matter. Carbon, oxygen, nitrogen, silicon. Other elements created inside stars or during stellar evolution can eventually become part of new clouds of gas and dust. Those clouds can form new stars, new planets, and potentially new worlds. In that sense, a nebula produced by the death of a star can also be the beginning of something else. Webb's infrared instruments allow astronomers to study these structures in remarkable detail. Instead of seeing only a glowing cloud, researchers can investigate different temperatures, chemical compositions, dust structures, and molecular environments. That turns an astronomical photograph into something much more valuable. A scientific record of how matter moves through the life cycle of stars. And then there are planets. Perhaps the most exciting targets are worlds orbiting other stars. One system that continues to attract enormous attention is TRAPPIST-1. The star is a small red dwarf located about 40 light-years away. It has 7 known rocky planets. Several of them orbit within or near the region where temperatures could potentially allow conditions suitable for liquid water, depending on their atmospheres and other factors. But there is a major problem. A planet being in the habitable zone does not mean that it is habitable. To understand whether such a world could support life, scientists need to know what its atmosphere is made of. That is where Webb becomes extremely powerful. When a planet passes in front of its star, some of the starlight travels through the planet's atmosphere before reaching Earth. Different molecules absorb specific wavelengths of light. By studying those patterns, astronomers can search for evidence of atmospheric gases. This technique is called transmission spectroscopy. It is incredibly difficult. The planet is tiny compared with its star. The atmospheric signal is extremely weak. And the star itself can produce activity that complicates the measurement. So researchers have to be extremely careful. A possible atmospheric detection is not the same thing as finding life. That distinction cannot be overstated. Scientists are searching for evidence. They are not simply looking for a headline. And that is what makes Webb so important. It allows astronomers to move from asking whether a planet exists to asking much more complicated questions. Does it have an atmosphere? What is that atmosphere made of? Is the atmosphere stable? Could liquid water exist? Could volcanic activity be occurring? Could the chemistry be compatible with life? And eventually, could we detect combinations of gases that are difficult to explain without biological activity? Those questions may take years to answer. But Webb has already changed the way astronomers can approach them. And the surprises aren't limited to planets and galaxies. Webb is also revealing how stars are born. Inside enormous clouds of gas and dust, gravity pulls material together. Dense regions collapse. Young stars ignite. Jets and radiation emerge. planets may begin forming around them. For visible light telescopes, much of this process can remain hidden behind thick curtains of dust. Infrared observations can penetrate those dusty regions and expose structures that were previously difficult to study. That means Webb is effectively opening windows inside stellar nurseries. And every new observation gives astronomers another opportunity to test theories about how stars and planetary systems form. There is another reason Webb's discoveries matter. The telescope isn't simply finding unusual objects. It is allowing scientists to connect different stages of cosmic history. The early universe. The first galaxies. The growth of black holes. The birth of stars. The formation of planets. The death of stars. The recycling of elements. And the possibility of life elsewhere. These aren't separate stories. They are pieces of one enormous process. The atoms in your body were not created on Earth. Many of them were forged inside ancient stars. The oxygen you breathe. The carbon in your cells. The calcium in your bones. The iron in your blood. These elements have cosmic histories that began long before our planet existed. Webb is helping scientists understand that history in greater detail. And perhaps the most fascinating part is that the telescope is still operating. Every observation adds more information. Every spectrum provides another chemical clue.